Thanks very much. So Scales is a 1 to 5 micron imager and 2 to 5 micron integral field spectrograph that's currently under construction. I guess the way to think about it is it has a pretty broad science case in that it sort of supplements what NERC2 can do right now with the imager and also adding on the IFS. It is an instrument that was designed from the ground up to be optimized for imaging exoplanets. So it's got a chronograph as well, and so we have a simulation on the left of that. We're also trying really hard to optimize our instrument and work with Keck to make sure it's good for twilight observing, sort of stuff that computers are doing. So the modes are up here, and one thing that's a little bit unusual compared to other exoplanet imaging instruments, because in the past, we have the imager, we have a low resolution integral field spectrograph, which is similar to things like GPI and charts. We also have a medium resolution spectrograph. It zooms into a very small field of view, kind of if you're looking very close to the star, or if you know where the planet is. So those are the overarching specs of the instrument, and there's more information in SPI if you're very interested. The integral field spectrograph, it's a little bit different than what people have done in the past. So for exoplanet imaging, lenslet arrays are really good because once you've gone through the lenslet array, you've sampled your field of view, and any aberrations you have in your downstream spectrograph don't matter. So we really wanted to have a lenslet array for exoplanet imaging. Obviously, the alternative is an image slicer, and that's really great if you care a little bit less about your aberrations, but you can get better spectral resolution because you can disperse the full length of the detector. We do something that's sort of a hybrid. So the low resolution mode uses the lenslet. The medium resolution R5000 mode, we use a lenslet and then a slicer in series. And then the lenslet samples your field of view, and the slicer just reorients the spot so that you can disperse the length of the detector. So that's a little bit unusual. Scales is under construction, well under construction at this point. So I'll take you through a few of the things we have. These are the mechanisms that we currently have in the lab. So this is a coronagraph stage, linear stage. This is the Leo stop wheel. You can see, if you have good vision, some Keck Leo stops in there. This is a tilt mirror that steers the planet or the star or whatever onto that small field of view and holds it there. This is a rotating cold stop. This is what we call the mode selector that switches between the low and the medium resolution mode. So all of these things have to work cryogenically. They have to work at room temperature so that you can build them, and then they have to work cryogenically. That's challenging, and some of these are still a work in progress. Here's some of the optics we have right now. So the gratings are in. We're still waiting on the prisms, but then we're getting to be near the end. That's a zoom in on the Leo stop. You can see nice little Keck people. All of our mirrors are diamond turned and gold coated, and then everything is made out of aluminum. So in principle, you build the thing out of aluminum, you get everything aligned, and then when you cool it, it all stays aligned. That's the idea anyway. Here's the lenslet array, which is all silicon. It's got that color because of the anti-reflection coating. And here are the integral field spectrograph filters. So at this point, we have almost all of our optics, and they are all meeting spec. So we're doing pretty well. The last optic that is just starting construction right now is the image slicer. And as you can see, it's kind of a beast. Same thing, all of these are diamond turned aluminum mirrors, gold coatings, and then slicers and things like that. So that's we're just starting to put metal on it. And that'll be the last thing to go in. And like Evan Kirby, I like to prototype out of cake. Thanks for setting me up on that. So this is an 18 slice image slicer cake. And we had a little review of it. The Keck AO folks came out and joined us over here. And yeah, we definitely passed this with you. The detectors. So the detectors we have 2 James Webb flight spares, or depending on your perspective, 2 James Webb flight rejects. And so these are 2 H2RGs from NearSpec. They're a little bit weird because James Webb is hardwired for 10-second readouts, and that's not fast enough for ground-based astronomy. So we've got some special firmware, and Peyton Beniak, who I see in the audience from UCLA, has been plugging these in and testing them out. And so just as of last week, this is an image of one of the detectors running cold with a 1-second readout time. So it's not tuned up yet, and I'm sorry, Peyton, for showing untuned image, but just from last week. And here is the detector package at UCLA. So the detector is behind the shielding right here, custom cable to the sidecar electronics, another custom cable, and that goes outside of the doer to the Macy electronics. So happy to see that moving forward. The big news is that the cryostat is here, so we have all of these subsystems, and we're now getting to the point where we can integrate it. Here's the cryostat with the members of the team who were willing to come at 5:30 in the morning when the cryostat came. So Steph Salem, who's our project scientist, Nick McDonald, who's our project manager, Maureen Savage, who's the UCO shops manager. These two guys drove it from New York. Dino Stelter, the instrument scientist, and me. And so this cryostat, it's working great. It's got extremely good vacuum performance. Here it is opened up. We've got all the holes in there. And so all of those modules that I've been talking, in principle, they just bolt into those holes and we're ready to go. So that's starting up now. So we're getting through the construction phase and into the integration phase. We have a monochronometer for a calibration system. So it's like a backwards spectrograph. This puts out 2 to 5 micron R of 10,000 light at a single wavelength. And we shine that in and we illuminate the lenslets, and that's how we do our calibration. So you get a point spread function at every wavelength on the lens array. It's a little different than how Osiris is calibrated, where you do one lens at a time and you do the whole spectrum. And here's Ephira Uni in the back for UCI, and it's her responsibility to figure out how to get this to calibrate the pipeline. Pipeline is underway, and so it's going to use the DRT framework. It'll make wavelength calibrated image cubes like this. You won't have to do that yourself, of course. It can do a quick look extraction in 20 milliseconds, and then it'll do sort of the science grade pipeline that'll take a few seconds to run. And the other exciting thing is that Keck is getting going, doing work at the summit. So here's Janet Hill. I think Rosalind took this picture. They're removing the NERV2 electronics, which is where our electronics rack is going to go. And in fact, they nailed us the NERV2 transceiver electronics rack. So we have that and we can start populating it. So to finish up, we're a 2 to 5 micron IFS and 1 to 5 micron imager for PET2AO. We have most of the hardware in hand and are doing the subsystem testing, and we're holding schedule, holding on for dear life for delivery next year. Thank you.